said, hey, you, let's do some Diffie Q. If something's looking blurry, then we'll bring it into view. I said, hey, you.
Check it out.
Welcome. Let's do some Diffie Qs. Today we're going to learn about Euler's method. This is an example of a numerical method. We would use a numerical method when it's either not easy or feasible to find a solution formula. For some differential equations, there may simply be no solution formula. So we have to approximate a solution, and to do that we use a numerical method. Euler's method is one such method. When we use a numerical method, it's important that we are not approximating a solution to simply a differential equation, but rather an initial value problem. The initial value gives us a starting point from which we base our approximation. Graphically, we might end up approximating a solution by computing a certain number of points, as we've drawn here, where we based this approximation off having a starting value in red here. So for reference, say there was an actual solution. It may be that that solution looks like this, and we can see that the approximated values are close to the actual solution, but may at some point diverge to some degree. Whether our approximated solution is close to the actual one is a question in of itself and deals with analyzing the error in our approximation. But let's see how we would actually come up with these approximated points even to begin with. So for Euler's method, we'll have an initial value problem, and as we've highlighted in our earlier explanation, we'll have a starting point, which we denote by x naught, y naught. That's the red point that we showed in the previous diagram. And then we'll have a differential equation that's first order written of this form. Now, here we have a blue highlight on the function f. We're going to think of that f as the slope, which indeed it is because we have a dy over dx. That slope is going to be important when we think about how this looks graphically. When we apply Euler's method, there is a decision that we need to make. Besides the starting point, we need to decide how wide the interval will be over which we do our computations. If we have a larger interval, it will amount to fewer computations. A smaller interval will be more accurate. Now, a key point of Euler's method is that it's really based around a single algorithm that's repeated. So when we talk about how to get from one point to the next, keep in mind that this is really the core of the method, and after you have this, you simply repeat it as many times as needed. So let's go ahead and look at a single iteration. To start with, we assume that we have a last point from which to base this iteration. We'll call that point x sub I and y sub I. Next, our new value, x sub I plus 1, is equal to the last x value that we've had, or the point that we are moving off from, and we add h to it, where h is the change in x. Graphically, it would look something like this, where if we have an x value, x sub I, to get to the next one, which will ultimately be called x sub I plus 1, the index increases by 1, we simply add h to it. And a good way to think about this is that we divide up the x-axis into intervals that are h in length. That is, for every single one of these intervals, we have h. And we'll keep moving over for x each time by h. So our next x value, even after this, which would be x sub I plus 2, will be x sub I plus 2h, or x sub I plus 1 plus another h. We're always increasing by h. If that made sense, the y value that we compute next, y sub I plus 1, will be computed somewhat similarly. The central idea is based on the blue slope that's from the differential equation. So imagine at this point, x sub I, y sub I, we compute the slope simply by letting x and y in this expression be x sub I, y sub I. We compute a slope, noting that this is a slope at this point, x sub I, y sub I. Now we travel along this slope until we are above the new x value. So if we move along this slope, we don't travel until we get all the way down here. We travel until we're right above h here. Let's color that new point green. Now the question is, how do we find the new y value? We know how to find the new x value. It's simply x sub I plus h, which we have here. But now the new y value, we can imagine how to find that. Thinking about this as a right triangle, where the slope is the hypotenuse of the right triangle, we have a base of h. Here we'd like to know what this is. Well, the slope is f of x sub I, y sub I, That's going to be equal to the change in y over the change in x, which happens to be h in this case. And now, of course, if we want to solve for the change in y, we'll multiply both sides by h. That tells us that the change in y is given as the product of h times the slope. So our new h will simply be the old one, and then we add the change in y to it. And our new y will simply be the old y with this change in y added to it. And now we will call the new point x sub I plus 1 and y sub I plus 1, which would here look like so. This is one iteration of the method, and you can see when it comes down to it, it's not that involved. We simply have one point here, and now we get a new point down here by really doing two computations. The first computation is very straightforward. We simply take the xi value we have up here, and we add h to it. And then the new y value is computed in a similar way, where we start with the old y value, and then we add not just h, but h times the slope. And graphically, that amounts to starting at this point, moving down the slope until we get to the new point. And we repeat this as many times as we want, as we move to the right and continue to create new points. Each time we'll compute a new slope. For instance, if we want to compute off of the green point to find another point, we would compute using another slope. Just as an example, that new slope might look like this. And following along this new slope, we might end up computing a new point, say here. And we continue with this process as many times as we would like. Now let's look at our first example. Here we have the differential equation dy over dx is equal to y squared over 3, and we have an initial value information, y of 0 is equal to 1. That means we have a starting point of 0, 1. Graphically, that looks like this. Now suppose we want to approximate y of 1 using a step size of 1/2. That means we're going to do two iterations. One to go from 0 for x value to 1/2 for an x value, and the next to go from an x value of 1/2 to an x value of 1. For our first iteration, since we start out at the x value 0 and we add the step size to it, that gives us a new x value of 1/2. That means that the next point is going to be over x equals 1/2. Now that point could be down here, it could be here, really anywhere, but it's going to be above or below the x-axis at x equals 1/2. And now we want to decide what is its height going to be, so we need to compute the new y value. That's going to be given by this formula here, where notice I've lined it up so that we see we're taking the previous point, 0, 1, in each case, and then we're adding to it something. In the x case, we're simply adding the step size, and that's the end of the story. In the y case, we're adding the step size times the slope, but notice they're very similar in format. Once we do that, for y, we get a new y value that's of 7/6, which is slightly larger than 1, which makes sense because this should be a non-negative and in most cases positive slope. So we should be increasing our y value as we go to the right. So we graph our new point, making sure that the y value is slightly above 1, and then we'll do our second iteration. We want to approximate a value when x is equal to 1. So let's do the iteration one more time, but the basic structure is exactly the same. Here, unsurprisingly, we have a x value of 1, and our y value will end up being this fraction, which is again larger than 1 and a little bit larger than 7/6. So let's graph the point. And to help drive home the fact that we're following slopes, let's graph the slopes in blue. So here we have a numerical representation with the final point, and we have a graphical representation here. Now our approximate y value when x is equal to 1 is 301 over 216. That's approximately 1.4. This is a separable differential equation, so we can find a solution formula. And if we do that and compute for that solution formula what the value is when x is equal to 1, we get this value, which is exactly equal to 1.5. Comparing that to our approximation, there's a percentage difference. That's about 6.7. Now, as we mentioned before, we have two steps here and got an error of 6.7%. But if we were to decrease the step size, we should get a more accurate result in general. Let's see what happens when we decrease the step size. So we're looking at the same differential equation, the same initial value, and we want to approximate the same y of 1, now using a step size of 1/4 instead of 1/2. I won't bore you with the calculations, rather I'll present them in a table. The last example has a more detailed outline of how to do the calculations, but they're exactly the same here. And now if we present these calculations graphically, in either case it's easy to see that our new approximated y value is 1.44, which is a little bit different than our previous approximation of 1.4. And as before, we knew that the actual was 1.5. And if we compute the new percentage error, we get about 4%. This is clearly better than the previous error of 6.7%. Now it's worth noting that error analysis is quite a big area of study in of itself. In this particular instance, we have a differential equation that's separable, so we can find the exact solution. Where numerical methods really shine is in the cases where it's too difficult or maybe even impossible to find a solution formula. So you don't have a hope of getting that solution formula. So you need some other way of finding out what the solution would look like. And if you don't have an exact formula to compare to, you need to know how far is your approximation from the actual solution. And that's where error analysis comes in. Now let's talk about some of the problems of numerical approximations in general. So the first problem is computation time. We can see just graphically there's a big difference between having a few solution points like this and having many solution points like this. So of course the more points, a clear picture, but it takes longer to do. In most cases, there'll be many points computed, and that can add up computationally. The next problem, there will be round-off errors where the computer has to round to be able to store the information, and by doing so will not fully capture the numbers that are being used to do the calculations. Over time, this roundup error builds and can be potentially a major reason why an approximation does not line up very closely to the actual value. And the last issue is stability. Depending on the differential equation, it may have unstable behavior near certain points. I hope you found this video helpful. We'll see you in the next video. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.